you. So let's get started with session 3, general topics. And the first paper we are going to have is learning latent representations to influence multi-agent interaction. So this is what Dorsa briefly talked about, and Annie Z will be presenting this paper. Annie, you can share your presentation.
All right, let me share my screen. Okay. Can you all see my slides? Okay.
Yeah, everything is visible.
Hi, I'm Annie, and our new work studies multi-agent interactions between robots and other non-stationary agents, such as humans. So before I talk about robots, let's first think about how people interact with each other. Specifically in this hockey example, the player on the left here is currently aiming from the right side of the goal. But the next time he approaches the goal again, he might pick a different strategy. For example, he might aim from the left side instead. And of course, this makes the goalie's job really difficult because this means that he has to deal with the different strategies of the opposing team during each offensive play. And so now similarly, when robots interact with humans or other robots, these other agents are non-stationary. They update their behavior in response to the robot. And so prior work for handling these multi-agent interactions would explicitly model the low-level policy of the other agent. But people can interact with each other with little to no effort. And they do this by keeping a high-level representation of the other person. And so we recognize that much like in human-human interaction, robots can also capture other agents with these high-level representations that change over time, which we refer to as their latent strategy. For example, consider these two robots playing air hockey. The ego agent on the left is a reinforcement learning robot that's tasked with blocking the incoming shots, while the other agent on the right is a rule-based robot that dynamically changes its strategy. And so the ego agent only observes the Y position of the puck as well as its own position. And to construct a non-stationary problem setting, the X position of the puck isn't provided to the ego agent, and instead has to be inferred from its earlier interactions. And so the ego agent can move its paddle up and down the X-axis, while the other agent has different strategies which correspond to aiming in different directions. Each trial lasts for a fixed number of time steps, and we define an interaction to be the resulting sequence of states, actions, and rewards of the agent. After each trial, the other agent will then select a new strategy based on the previous interaction. And importantly, the ego agent never observes the strategies or the actions of the other agent. So because naive reinforcement learning algorithms assume that the environment is stationary, they don't actually model the changing environment. And so when faced with a non-stationary agent, such as this one, the RL agent will learn to just pick one mode to block, and here it blocks on its left side. So for the robot to be able to adapt to the other agent, it first needs to model how its behavior is changing. While prior work focused on estimating the policy of the other agent and how that changes, our approach instead learns a high-level representation of the other agent, which can change over time. To learn this representation from data, we train an encoder that takes in the previous interaction and predicts the next interaction's latent strategy. Then from this representation, the decoder reconstructs the rewards and transitions of the next interaction. And the whole point of this latent representation, Z, is to capture what the other agent will do next. So we train this encoder-decoder model to maximize the log likelihood of the rewards and the transitions that we're seeing across all of the interactions. And so having learned a model of the other agent, we can now train a policy that's conditioned on the predicted latent strategy. This policy will give us different behaviors for different predictions. And so it basically gives the ego agent the ability to react to the other agent. Now to recap, during training, our approach first trains an encoder-decoder model to learn a representation of the other agent. Then we train a policy conditioned on this representation so that the agent can react to the other agent. Now putting all this together during a new interaction, the encoder predicts the other agent's latent strategy. The ego agent then carries out the policy conditioned on this prediction, and this process repeats. So we call this whole framework learning and influencing latent intent, or LILI. We first considered a simple navigation task here with the ego agent represented by teal and the other agent represented by gray. The ego agent always starts each interaction at T1, while the other agent sits somewhere along the shaded blue circle. And during each interaction, the ego agent needs to capture the other agent as quickly as possible, but it never observes the position of the other agent and only receives reward based on how far they are from each other. The other agent is only allowed to move between interactions, and specifically it moves either clockwise or counterclockwise, depending on whether the ego agent's final position is inside or outside of the circle. Here we visualize the trajectories taken by the ego agent in teal, where the teal circle represents the final position of the agent, and each frame corresponds to a single interaction. So this first policy is trained with soft actor critic, which is a standard reinforcement learning algorithm that doesn't model the other agent. And this policy at convergence moves to the center of the circle in every interaction. And that's because without knowledge of or any mechanism to infer where the other agent is, the center of the circle is where the agent receives the highest reward. In contrast, our method, LILI, successfully models the other agent's behavior and can capture the other agent in each interaction. But notice that the other agent is captured along this lower part of the circle. If the goal is to reach the other agent as quickly as possible, then ideally the other agent should be positioned at the top of the circle, where the ego agent is closest. So in other words, the ego agent should influence the other agent to move towards that blue region. So instead of simply reacting to the other agent, what we actually want is to learn a policy that can influence its strategy. This influential behavior can be learned by maximizing the long-term rewards across interactions. And this objective naturally motivates the ego agent to act in a way that leads to more desirable future strategies in the other agent. And so now returning to the navigation example, as expected, we see that the LILI agent with influence learns to trap the other agent at that top of the circle. This is where the target is the closest to the ego agent and where it receives the highest rewards. And we see that again here in this plot of the rewards collected during each interaction. LILI with influence almost matches Oracle performance, while LILI without influence earns slightly lower rewards. In this next task simulated in Carla during each interaction, the ego agent, which is controlling the blue car, needs to pass the other agent, which is controlling the tan car. The other agent recognizes that the lane the ego agent passes in is faster, and so it'll merge into this lane during the next interaction. The converged soft actor critic agent changes to the left lane in every interaction, even when the other agent moves to the left lane too. And this results in near collisions. On the other hand, LILI correctly anticipates the lane that the other agent will switch to, and it'll switch to the opposite lane accordingly. And because the strategies in this setting are equally rewarding to the ego agent, here LILI without influence results in the same performance as LILI with influence. Finally, we tested our approach in the air hockey game described earlier. So as a reminder, the other agent strikes the puck either to the left, down the middle, or to the right. And after each trial, the other agent will select a new strategy based on the last interaction. Specifically, it always aims away from where the ego agent last blocked. So the ego agent earns +1 reward for blocking the puck. And now let's pretend the robot has an easier time blocking on its left side for some reason. And so it earns +2 reward for blocking shots that come down the left side. And this means that influencing the opponent to aim to the left side more often will lead to higher long-term rewards. So we first trained a policy with soft actor critic. And again, because it doesn't model the opponent, this agent learns to block only one mode, which is its right side. And near the end of training, it switches to blocking left instead every time, which earns it higher rewards. And here, instead of rewards, we plot the success rate over training, and we see that the final policy achieves about a 40% success rate. However, we see that Lily can block a lot more successfully than soft actor critic, but it doesn't always get that bonus reward for blocking left. And that's because it's not explicitly trained to influence the other agent's strategy. Lily blocks successfully about 90% of the time. And finally, we look at Lily with influence. So this agent, as we can see, can manipulate the other agent to alternate between left and middle shots. And by doing this, it achieves higher overall rewards. So looking at success rate only, we can see that Lily with influence has a similar success rate as Lily without influence. But where we actually see a difference is when we look at how frequently the opponent fires left, middle, and right. Lily with influence leads its opponent to fire left the most often, 41% of the time, while without influence, the distribution over the strategies is uniform. So we tested the policies learned by a soft actor critic and Lily against a human expert. So this human expert follows the same set of strategies as the robot opponent, but here the human has imperfect aim. The soft actor critic agent's success rate is 45%, while Lily's is 73%. So to conclude, we can often capture the behavior of non-stationary agents with these high-level representations. And with these representations, the agent can learn to anticipate and influence other agents across repeated interaction. Thank you.
Thanks, Annie. Good talk. So I have a question for you. So the question is, when talking about multi-agent setting, are we focusing on collaborative scenario or a competitive scenario or an interaction scenario?
Yeah, so this framework isn't specific to collaborative or competitive scenarios. We're looking at any setting where there are two agents interacting with one another. And the nature of the interaction basically has to be encoded in the reward function. So for example, in the point mass navigation task, the ego agent is rewarded to capture the other agent. And so in that sense, you can view it as perhaps a competitive scenario.
Okay. So if there are no other questions, I will ask one question. So in the scenario that you are modeling long-term interactions, did the variance of your reinforcement learning updates increase because of the increased time horizon? And if so, then how did you model it?
Yeah, it actually did. So for example, in the point mass navigation task, oftentimes, especially in the middle of training, when it was still trying to capture the other agent to that top of the circle, it would sometimes lose track of the other agent. And that's where the rewards would drop again. And essentially one thing that we did try was instead of treating it as one long sequence, all the interactions as one long sequence, we would segment them so that we had, I guess, shorter sequences of interactions. Okay. And that still led to that influential behavior, which was nice.
So we have a couple of more questions, but I don't think we'll have time to cover them. But let's thank Annie for her talk, and feel free to get hold of Annie to get your questions answered. And now we will move on to the next speaker. So our next talk is on flexible skill formation with learning from demonstration and reinforcement learning via representation sharing. And Meet will be presenting this talk. So Meet, take it away.
Thank you, Professor Agrawal. I hope you can see my slides. Okay. Hello again. I am Tulan Akbulut, a master's student from Boğaziçi University, Istanbul, Turkey. I'm supervised by Erhan Öztop and Emre Uğur. It's my pleasure to present our work here. We shared the code and data of this work on our project page. Learning from demonstration is a widely used method to teach robots dexterous skill. However, the performance of the robots depends on the demonstration distribution. Let's assume that 6 demonstrations are given to an LFD model. After training with these demonstrations, when the model is requested with the black dot to perform the skill within the demonstration range, it can generate the required black trajectory. However, if the required trajectory should follow a path outside the demonstration range, task requirements may not be satisfied and further adaptation is required. In this work, we study following challenges in adaptation during task extrapolation through trial and error and skill transfer. The relations between task parameters and trajectories are often highly nonlinear and complex in real-world problems. Therefore, excessive policy updates may be required for adaptation. However, experiments with real robots takes time and resources. Another challenge is preserving demonstrated behaviors automatically during adaptation, because it can be more practical than to encode these behaviors in a reward function. These behaviors can be related to safety, robot and environment constraints, or other user preferences. Skill transfer becomes extremely difficult when it happens between robots with different embodiments. In this case, additional engineering efforts are required to find correspondences between policies. In literature, state-based correspondences are sought to transfer the policy, but this approach requires state pairing beforehand. We propose adaptive conditional neural movement primitives called SCNMP to address these challenges. We use conditional neural movement primitives as the base LFD model to learn skill representations, because this state-of-the-art model can learn nonlinear relations between trajectories and task parameters using only a few demonstrations. Let's have a look at how representations are found. This framework consists of one encoder and one query network. Random number of observations from sensor motor trajectories are passed through the encoder network to get corresponding representations. Then these representations are merged to find the trajectory representation. Using this representation, the query network produces parameters of a Gaussian for queried time steps. It's also possible to condition this Gaussian distribution with external task parameters. So at test time, the model generates the trajectories by querying all time points for given task parameters and observations. Finding trajectory representation from random observations and trajectory generation with respect to task parameters are two important features we exploit in our framework. In order to achieve the goal with given task parameters, CNMP model is conditioned with these parameters to generate the required trajectory. Then the generated trajectory is given to robot execution. If the robot does not achieve the task, reinforcement learning agent is triggered. The RL agent is initialized with the same LFD model. And this network updates its internal parameters via reinforcement learning, which is alternated with error-based supervised learning. For observation and task parameters coming from the demonstration set, supervised learning loss is used. When the inputs are coming from extrapolation cases, the same network is updating by the policy gradient loss. In practice, this allows the system to generate novel trajectories that are encoded into the same latent state with demonstrations and share similar characteristics with them. After the RL agent finds the satisfying trajectory for the new task, this new trajectory is fed back to the LFD system as a new demonstration. Afterwards, the loop continues. Our framework improves itself at each cycle and becomes less prone to failure. In skill transfer scenario, both robots have their own SNMPs and they form a common latent space during learning from demonstration. Here, an additional mean square error loss is defined to make corresponding representations similar. Our representation learning method can handle different number of joins and different number of observation points because it finds the representations at skill level. Therefore, no time warping or state pairing mechanisms are required. In this part, task parameters are not used not to involve any biases about the task. At test time, skill transfer for a novel task can be achieved by transferring skill representation from the first robot to the query network of the second robot. Afterwards, the target agent can perfect the skill using its RL agent. We made 4 simulation and 2 real robot experiments. The first experiment is the working example where aim is to extrapolate to a novel viewpoint outside the demonstration range. LFT on the model cannot generate a trajectory that goes through the specified point. RL on the model generates a trajectory that maximizes the reward but does not preserve the demonstrated shape. The generated trajectory by SCNMP achieves the task while preserving the shape. In order to evaluate our model's adaptation capability to novel goal points while controlling a robot, we adapted this experiment from Stark et al. And compared SCNMP with their state-of-the-art post-adaptation method. 9 demonstrations of pushing the black obstacles to a goal point are provided to a 3-degree of freedom planar robot. Then the robot is requested to push the black obstacle to a novel goal point. Here, baseline uses 1 movement perimeter model for each goal position, whereas we can use a single model for all goal positions. On the left, demonstrations are shown. And on the right, you can see the performance of the pure LFT model and the performance after adaptation. As shown with the blue plot, our model finds the successful trajectory or requires small adaptation for all interpolation goal points. For the extrapolation goal point, SCNMP achieves the task around 60 iterations. As shown in the table, SCNMP requires order of magnitude fewer samples than the baseline to adapt. In this experiment, the aim is to evaluate our model's adaptation capability to novel environments. The experiment is adapted from Everton et al. For comparison with their state-of-the-art adaptation method. The aim is to produce a trajectory that starts from the fixed blue point, avoids the randomly positioned wall, and ends at the randomly selected red goal point. Demonstrations are given for 30 environments. Sample demonstrations are shown on the left. The performance of LFT on the model and SCNMP is shown together in the video. As shown in the graph, the baseline and our method are competitive in terms of the number of environments used. However, if we plot the same graph with respect to sample trajectories used, we see that SCNMP requires many fewer samples than the baseline for each environment. This table illustrates that SCNMP is order of magnitude more sample efficient than the baseline for a single environment and for the whole task. We implemented 2 experiments to test our model's performance with real robots. First task is obstacle avoidance task, where task parameters are object height and wall height. Here the challenge is learning nonlinear relationship between parameters and 6-degree of freedom complex trajectories to adapt novel heights. Second task is a marble pouring task. Task parameters here are weight of container and desired pouring amount. Here the challenge is generating motion trajectories from weight-based rewards to pour a novel desired amount. The last experiment aims to evaluate the transfer learning capability of SCNMP. We adopted this experiment from Gupta et al., where 2 robots with different morphologies are provided with proxy skills to learn how to transfer policies. Given that 3-degree of freedom robot has the skill to achieve a button pressing task, 4-degree of freedom robot should benefit from its experience and acquire the skill quickly. Note that this task is extremely hard to learn from scratch because the robot does not receive any reward unless it can touch the button. 3 proxy tasks, reaching, pushing, and peg insertion, are used to form a common latent space. Pushing task is shown on the left. For the test task, a demonstration is provided to 3-degree of freedom robot, and 4-degree of freedom robot is expected to approximate the skill by skill transfer. For 12 demonstrations, how common latent space is formed is illustrated. Our model finds representations at skill level, 12 representation clusters for 12 skills, therefore does not require additional state pairing techniques. The effect of common representation and reinforcement learning is shown here. For the robot almost acquires the skill after transfer, and our RL method is used to perfect it. In conclusion, we propose adaptive conditional neural movement primitives that is order of magnitude more sample efficient than the state-of-the-art methods. It preserves demonstrators shaped by training with demonstrations continuously, and it enables skill transfer between robots with different embodiments by finding a common latent space at skill level without explicit time warping and state pairing. Thank you for listening. I would like to answer your questions.
Thanks for your talk, Meet. So if people have questions, feel free to post them in the Q&A, and I'll be happy to read out those questions. In the meantime, so one question I have is, can you maybe highlight the key differences between AC and MP and say a variational autoencoder in learning the motion primitives?
Okay, I can do that. I want. Okay, here it is. The main difference from a traditional autoencoder is that here the input number is changing. The observations from this trajectory are coming from random points, and also its number is also random. These observations are passed through a parameter sharing encoder separately, and afterwards these representations are merged to find the trajectory representation. Therefore, it can increase its own data set by taking random permutations from these trajectories.
Okay, thanks. So I have a follow-up question from Jackie. Are there failure modes or disadvantages of using conditional neural processes versus other models?
In my experience, conditional neural primitives or this conditional neural primitive method can map task parameters to trajectories better than the other movement primitive methods. Therefore, I think our approach requires fewer samples than other methods.
So is there any disadvantage of using your approach as compared to other approaches?
Oh, okay. Is there any disadvantage? I think I can answer this one later because I'm not sure.
Okay, no worries. And one last question. So in the 3 degree of freedom and the 4 degree of freedom experiments that you showed, of the pushing task and the pressing the button task, so did you need any alignment when the pushing task was being done, or no alignment?
No, like the thing is that we don't need alignment, but like the time vector is normalized between 0 and 1, but like warping alignment, like dynamic time warping, is not required because, as I said, the latent space is formed at skill level. So like the observations are coming from random time points, etc. So for each skill, I obtained one representation. Therefore, I'm not worried about how they behave with respect to time.
Okay. Thanks a lot for your talk.
Thank you.
I encourage everyone to catch hold of the speaker if you have more questions. And now we will move on to the next presentation. And that is learning from suboptimal demonstrations via self-supervised reward regression. And that will be presented by Lotte. So Lotte, take it away.
Yeah, sure. Thank you, Professor Agrawal. Can you see my screen?
Yeah.
All right, thank you. Okay, so hello everyone. My name is Latent Chen. Today, I will present our paper, Learning from Suboptimal Demonstration via Self-Supervised Reward Regression. This work is done in co-robotics lab with my co-author, Rohan Palaja, and my advisor, Matthew Gamble. Researchers are developing robots for application in healthcare to manufacturing, scientific discovery, and even assistive household tasks. However, traditional design for task controllers requires an army of robotic experts for each task, greatly limiting the possibility of robots. In contrast, learning from demonstration techniques empower end users to program robots to achieve their personalized goals without robotic expertise. Humans are often able to give instinctive but suboptimal demonstrations that could be leveraged for robot learning from demonstration. This suboptimality is often due to diverse heuristics humans develop to compensate for cognitive limitations. However, LFD research often assumes access to optimal demonstrations and generally cannot do better than the demonstrations, even if they are suboptimal. Preference-based RL bypass the requirement of optimal demonstrations, but queries humans for preference, which is a cost-intensive process. In our paper, we produce a new state-of-the-art learning from suboptimal demonstration by first characterizing the relationship between a policy's performance and the amount of noise injected. We characterize the relationship via a low-pass filter. Our reward learning framework, SSR, then learn from this more accurate noise performance relationship. We further propose a more robust noisy trajectory synthesizer, noisy ARL, to handle covariate shift for both the policy and the reward of ARL. Lastly, we show SSRR achieves a higher accuracy in reward learning, and the trained policy achieves a higher performance than suboptimal demonstration and previous state-of-the-art DREX. We also demonstrate our algorithm in a robot table tennis topspin strike task as shown in the video. So first of all, why do we need noise injection? PBRL and T-Rex could learn from the suboptimal demonstration by explicitly asking humans for preference. DREX, however, avoids the requirement and automatically generates the ranked trajectories by injecting varying levels of noise eta. Injecting noise means transforming a policy pi to be eta greedy policy pi eta, which draws a random action with probability eta. DREX achieves automatic ranking by assuming that the higher the noise level is, the lower the trajectory should be ranked. Next, let me introduce what the noise performance relationship is. Here is an optimal policy trained by software actor critic on half cheetah. If we inject the noise into the policy, the performance will drop. And with more and more noise injected, the performance becomes worse and worse. But how does the performance degrade with varying noise levels? Is it a linear relationship, an exponential relationship, or a logarithmic relationship? The noise-free policy achieves a high ground truth reward of almost 9,000. The 0.3 noise policy achieves a reward of 3,000, and the last two achieves even lower reward. If we plot the corresponding noise performance data points, we could obtain a noise performance curve, which in this case is a decay-like relationship. This is what we call the noise performance relationship. Prior state-of-the-art DREX works by 4 stages. First, it employs behavioral cloning to obtain a policy from the demonstration state action pairs. Second, DREX inject varying levels of noise into the behavioral cloning policy to create noisy trajectories as we introduced. Third, DREX automatically generates ranked trajectories by noise level ranking. And finally, DREX learns a reward function from the ranking information by the loose shepherd rule. We argue DREX has two key drawbacks. The first one is behavioral cloning, which suffers from covariate shift when synthesizing noisy trajectories, which means the policy error compounds and the agent gradually enters a state space that never occurs in demonstrations. It will make the agent choose random actions and result in even more far away from the desired trajectory. The second one is unhelpful inductive bias from loose shepherd rule when learning from the binary rank information. For example, if we apply loose shepherd rule to the three-level noise eta0, eta1, and eta2, and their corresponding trajectories tau0, tau1, and tau2, the resulting reward of tau1 will be the average of the reward of tau0 and tau2, which means a linear noise performance relationship. No matter what the noise levels are, what the environment is, and what the policy is. In our paper, we first characterize the noise performance relationship. To do it, we first train a policy with an DIRL algorithm and then inject noise and calculate the performance at each noise level, as we did for half cheetah. We can repeat the process for other environment and policies trained with other DIRL algorithms. As we could observe, the noise performance relationship is heterogeneous, which is contradictory to loose shepherd rule's assumption. If we apply loose shepherd rule blindly, it sometimes, in some situations, it might fit well, but in most cases, it won't fit the actual noise performance relationship. However, a sigmoid function could well capture the noise performance relationship and adjust it to different environments, policies, and the noise levels. In our method, we utilize ARL to obtain an initial policy and an initial reward, which is a learned reward from the ARL discriminator. We then generate the noisy trajectories through interaction with the environment, and then criticize the noisy trajectories by the initial reward. Through this way, we could get a sense of how performance degrades with varying noise levels. We can then send through a low-pass filter to characterize the noise performance relationship. In our case, we utilize the sigmoid function, as our experiment shows it could capture the noise performance relationship very well. We could then train a reward function by regression to the sigmoid function. Since ARL's initial reward R is biased to evaluate its policy, evaluating R on noisy trajectories may not be reliable because of covariate shift. Therefore, we propose noisy ARL, which injects noise in ARL's training so that ARL is more generalizable to the state space, and we employ importance sampling to adjust the discriminator loss due to the change of sampling process from policy pi to the noisy policy pi eta. The two steps in noisy ARL provides a more robust reward and policy learning, enhancing the ability to accurately characterize the noise performance relationship. We carry out our experiment comparing with the benchmark DREX by a 3x2 experiment design. The noisy trajectories could be generated via three different methods: behavioral cloning, ARL, or noisy ARL. And we apply either SSRR or our benchmark DREX to learn from the noisy trajectories. We compute the correlation between the learned reward function by SSRR or DREX with the ground truth reward shown in the table. SSRR learning with noisy ARL noisy dataset generation achieves the best correlation across the 6 combinations. We could observe DREX performance fluctuates a lot with different noisy dataset generation methods, further showing that the noise performance relationship is heterogeneous. And when the relationship fits loose shepherd rule's assumption, it can work well, while when it doesn't fit well, DREX performs poorly. In contrast, our method adapts to different noise performance relationship via the flexible sigmoid function, achieving relatively stable performance. We further show the correlation plot of SSRR and DREX performance on half cheetah. The red dot represents the original demonstration. The blue dots represent the datasets in the noisy dataset, which is the training data for SSRR and DREX. The green dots are unseen test data. We could observe that SSRR preserves the reward structure far beyond the demonstration point, while DREX twists the reward structure. We further utilize the software actor critic to optimize policy on the learn reward function and show that SSRR's policy outperforms the suboptimal demonstration and the DREX. We further demonstrate our method in a robot table tennis setup. The task we wish to accomplish is a top spin strike. In demonstration, humans give suboptimal demonstration with lower speed and spin, which are represented by return lateral speed and vertical acceleration respectively. AIRL could replicate the demonstration with a little lower lateral speed, but is unable to achieve a better performance than the demonstration. SSRR, however, performs significantly higher speed and spin than both the suboptimal demonstration and the AIRL policy. In conclusion, we developed self-supervised reward regression, a framework to learn from suboptimal demonstrations. We illustrate its superior performance through its capability to learn a more accurate noise performance relationship and a more robust noisy data synthesizer. Thank you. I would love to answer any questions.
Thanks, Lotte. So if anyone has questions, feel free to type in the Q&A box. In the meantime, one question I have is there any intuition that you have why the sigmoid function works better than the loose shepherd? And are there any failure cases that you know where the sigmoid function does not matches the noise characteristics?
Yes, that's a good question. So the reason why we choose the sigmoid function is that we first plot the noise performance relationship for several different policies and environments, and observes that it could will capture the sigmoid function will capture the trend, and while the loose shepherd rule is constant for all the different environments and policies. For your second question, what's the failure case where sigmoid function could not capture the result, could not capture the noise performance relationship well, is here I give two possible counter examples. So first one could be tasks that with a little noise injected, the performance will drop abruptly so that it doesn't conform to a sigmoid function. Another counterexample is when you give a total failure demonstration, like a super suboptimal demonstration, such that adding noise will not degrade the performance further, then the noise performance relationship will just be a flat line, and SSRR cannot do better than demonstration in this case either.
Okay, thanks, Lotte. And if there are no more questions, we will move on to the next talk. Let's thank the speaker once more. And the next talk is Domain-Invariant Robot Learning for Sim-to-Real Transfer. And the presenter is Ajay Tanwan. Ajay, you can take it away.
Thanks, Pulkit. Yeah. Hey guys, I'm Ajay Tanwani. I'm postdoc at UC Berkeley. In this work, I'll be presenting a domain-invariant robot learning approach to adapt deep models to new environments where the testing data is drawn from a different distribution as that of the training data, such as in transferring models from simulation to the physical world. Collecting and labeling large-scale training data in physical environments is time-consuming and cumbersome. Generating this data in simulation provides a feasible alternative, as it is also evident by a number of papers that were presented at CoRL this year. But the caveat remains that the modeling inaccuracies do not generalize to the physical world. In this work, we investigate how we can mitigate these discrepancies across domains, in particular across image and object distributions for downstream tasks such as vision-based decluttering. In contrast to widely used domain randomization approaches that naively treat the discrepancy between the domains as variability in the simulation parameters, we focus on sample-efficient, feature-based domain adaptation methods to learn invariant feature representations for transferring to a new environment. More formally, we analyze the situation with two domains, one corresponding to the simulator or the source domain, and the other corresponding to the real or target domain. The simulator domain has lots of labeled examples, while the real or target domain has very few labeled examples, but can have a lot of unlabeled examples. And we seek to learn a policy such that the empirical error on the target domain is minimized. And the policy here is represented by a concatenation of the functions f and g. Since the two domains are different, there's a mismatch between the joint distributions of the source and the target domain. Commonly used domain adaptation approaches learn an invariant feature transformation by aligning the marginal distributions across domains, that is at the source and the target distribution. They implicitly assume that the conditional distributions of the transform features also remains similar across domains as shown in this side of the figure. Aligning the marginal distributions only, however, can create ambiguity in class alignment that can result in a negative transfer to a new domain. To this end, we present a domain-invariant representation learning approach that semantically aligns both the marginal and the conditional distributions by leveraging upon a few labeled examples of the target domain. The joint discrepancy across both the domains is minimized by minimizing the sum of the marginal discrepancy and the conditional discrepancy across domains. So the marginal discrepancy here refers to the distance between the probability distributions of the transform features in the shared feature space, whereas the conditional discrepancy refers to the resulting distance between the policy distributions at the output level. To make it concrete, let's consider this two-dimensional synthetic example with two classes as shown in orange and blue. Filled circles in this example represents the labeled examples, while the empty circles are unlabeled examples. In the conventional supervised learning scenario, we see that the decision boundary in black on the right plot fits well to the training data, but does not generalize well to the target data drawn from a different distribution. Aligning the marginal distributions in the shared feature space as represented by these overlapping density plots, however, results in a cross-mapping of class categories with negative transfer. Intuitively speaking, the apples of a simulator are being aligned with the oranges of the real domain in this case. Even if there exists a label shift with an imbalanced class ratio in the target domain, such as that of 0.1 in this example, that is the ratio of class categories between the source and the target domain, we see that it leads to uneven mixing of class samples across the decision boundary, with the constraint being put that the marginal distribution should align in the shared feature space. Now, DIRL addresses the cross-label mismatch and the label shift problem by aligning both the marginal and the conditional distributions with a few labeled examples in the target domain, as seen here with these overlapping contour plots, as well as the density plots in the shared feature space. So the main idea behind DIRL is that we are using a few labeled examples as anchor points and drawing the respective unlabeled target distributions towards them to mitigate the conditional discrepancy across the domains. This main idea is grounded in theory as well. The most well-known result in domain adaptation is from Ben David et al. In 2010, which suggests that the target domain error of a policy is bounded by the sum of the source error, the marginal discrepancy across domains, and the error of the best performing model. That is the model that gives the lowest error jointly in both the source and the target domains. This best model error is conventionally assumed to be small in unsupervised domain adaptation approaches. More appropriately, this best model error term can in turn be formulated as the cross-domain performance error of the optimal policies, which is represented here by the cross-overlapping area between the class categories in the shared feature space. And this area would be non-zero for cross-label mismatch or the label shift examples that we presented, which in turn are representing the conditional discrepancy between these distributions. So the target error is therefore bounded by the marginal and the conditional discrepancy across domains that DIRL seeks to optimize. The overall algorithm optimizes 3 additional loss functions on top of the policy loss. One is the marginal alignment loss, which is optimized with adversarial learning by using a domain discriminator to distinguish between source and target examples. The conditional alignment loss is also optimized with adversarial learning for each class separately by using a few labeled target examples and predicting pseudo labels for the unlabeled target examples if required. And third is the triplet distribution loss, which makes the conditional distributions disjoint in the shared feature space. In contrast to working on the individual examples, the triplet distribution loss operates on distributions of positives and anchors belonging to the same class, whereas the negative distributions are centered on examples belonging to a different class. Let's first benchmark the performance of DIRL on digits datasets, that is MNIST, MNIST-M, SVHN, and USPS. In these source to target configurations, we train the model on labeled source and unlabeled target data and evaluate the results on a held out target set. We compare the performance with reconstruction-based domain adaptation approaches, DAN, which aligns the marginal distribution across distributions, triplet loss, associative domain adaptation, and MCD, and a few shot and domain adaptation and DAN for semi-supervised scenario. The results suggest that MCD performs better among unsupervised approaches by minimizing the conditional distribution discrepancy across domains, but it suffers in problems with large domain strips such as USPS to SVHN or MNIST to SVHN. DIRL consistently gives better performance across all these problem statements in comparison to the unsupervised and semi-supervised domain adaptation approaches in handling large domain shifts. TSNE visualization results suggest that DIRL compactly represents the class distributions across data sets better in comparison to DAN that only aligns the marginal distributions and the no adaptation scenario. All right, let's now turn our heads back to investigate the feasibility of vision-based decluttering by sim-to-real transfer with the proposed approach. To do so, we generate about 20,000 simulation images using publicly available object meshes in the simulator that is split across 12 object categories. Similarly, we collect about 200 real images with the mobile Toyota HSR using commonly available household and machine shop objects that you see on your right. So the robot declutters the environment by first recognizing the objects on the floor and subsequently planning the grasp points to pick them up and deposit them in the target bins. So there are 2 networks involved here. The grasp planning network is learned on top of synthetic depth images using the simulator data only. The grasp labels are obtained by evaluating the grasp samples under robust wrench resistance metric, which is used to evaluate the grasp success probability. As used as the ground truth labels. And the object recognition network combines the data from the 2 domains using the DIRL approach. We modify the base architecture of single shot object detection network to add domain and class conditional domain classifiers on top of the feature pyramids. Results here indicate results for the deep object recognition network here indicate that naive transfer of models from simulation to the real results in a poor performance with about 26% accuracy only. Naively combining sim and real data is also suboptimal, whereas triplet, DAN, and MCD improves the performance in transferring to the real environment. DIRL mitigates both the marginal and the conditional discrepancy for more robust sim to real transfer. Experiments on Toyota HSR show that the robot is able to grasp a wide variety of objects with about 86.5% accuracy, in contrast to 76% with a PCA baseline grasping policy. The video here shows the real implementation with the Toyota HSR. We randomly drop a subset of real objects on the floor. The robot recognizes the objects, plans the grasp, and puts them in the target bin. The objects are allowed to overlap after they fall down on the floor. In case the objects overlap by more than a certain threshold, the robot executes a singulation primitive to isolate these objects, and subsequently plans across these primitives to declutter the floor in a repetitive manner. All right, in our ongoing work, we are extending DIRL to handle conditional distributions mismatch in continuous spaces, such as in smoothing or folding tasks with cloth or fabric. We are interested in learning domain-invariant models across multiple environments with a fleet of robots, and also to close the real-to-sim gap in learning generalized models across new domains. The main takeaway of this work is that domain randomization is a promising approach, for sim to real transfer, but one should not stop there. Incorporating the real data by aligning the marginal distributions can lead to performance improvement, but may also result in negative transfer with cross-label mismatch or label shift that we highlighted in this study. We introduced DIRL that semantically aligns both the marginal and the conditional distributions for provably efficient domain adaptation. And presented as use case for a real robotics application. So yeah, I'm happy to take further questions at this point.
Thanks a lot, Ajay.
Awesome.
So one question from Nimrod is a follow-up to what you were discussing about extending to continuous action spaces.
Yeah.
So, I mean, do you have any concrete suggestions on how to apply this method to regression instead of classification problems?
Yeah, we've been looking into this problem as well. I'll suggest you to drop in the extended session because the answer is slightly longer, but you can apply this discriminator at the domain level, at the feature transformation level, but at the policy head, you can also use a similar state action discriminator, or even if there's the dynamics mismatch, you can use a state action next state discriminator as well. So instead of using K per class discriminators, you would have to rely on some form of instance reweighting here, which we are investigating at this point for extension as well. So you can use it, but it's a little bit different formulation, which I can probably present the block diagram in the extended session.
Okay, I have one more question. So did you apply DRL just for object detection or for grasping as well in the decluttering task?
Yeah, thanks for this question. So far in this study, we reported the results for the object detection or recognition part. We have investigated for the grasping problem as well. The results seemed more robust because the depth image proved sufficiently robust in transferring across the kind of examples that we saw. But in other examples, we see some promising aspects in applying it across depth images as well. So the results here were for the object recognition network only. Okay.
And one last question I have is, so you talked about in domains where there were no target labels, you generated fake labels. So can you say a bit more about that?
Yeah, that's a great question. So we applied this for a few domains. One was this 2D synthetic domain, the digits domain, and then the object recognition domain, and there's some other studies as well. So for most of them, we did not have to use the pseudo labels, but for instance, for the object recognition network, we had to use the pseudo labels after pre-training the source network. and using them to further align the conditional distributions. So it's an interplay between aligning the conditional distributions, which requires more robust labels, in contrast to the marginal distributions alignment, which comes in a way for free because of the source and domain, target domain labels. And this interplay is somewhat domain dependent. So you may have to tune this part in terms of how much pseudo labels are required in comparison to using just a few labeled examples that you can provide as an outset.
Okay. Well, thanks a lot. Yes, thanks a lot, Ajay. And again, I encourage everyone to get hold of Ajay in the extended sessions. And with that, we will close this session, and I will hand it over to Claire.